Okay, so I'm very happy to have Rani out from Tel Aviv University speak today. We'll talk about improved lower bound for the Fourier entropy or influence conjecture via lexicographic functions. Rani recently started as a faculty at Tel Aviv University. He was a postdoc here at the CMSA a few years ago, so it's very nice to have him back here. Please.
Thank you, Umri, for the kind introduction. Indeed, I would have loved to come in person and visit you all in Garden Street, but the building is closed and there's the pandemic outside, so maybe it's not such a good idea. I do miss now it's the mid of October, all the fall foliage, the red, the crimson leaves around, that must be beautiful. Perhaps next year. And thank you for coming to the talk. So this is a very long title. We'll explain everything step by step. And let me start with some basic definitions. So we're talking about Fourier analysis of Boolean functions. So by this, I mean that the inputs, you see, this is not just any vector. The inputs are true and falses, or we have plus and minus ones as the inputs. Plus one is kind of false, and minus one stands for true. Any such function can be expressed not just in the regular basis, but in the Fourier basis. So this is, you have the definition of the basis functions here. These are just multilinear polynomials, monomials, and you can sum them with various coefficients. And we have the definition of the inner product. This is just the expectation of over the uniform distribution of the pointwise multiplication of the two functions. This is a vector space. This has dimension 2 to the n, so we need 2 to the n basis elements, and we label them by subsets of 1 to n. So this f hat of s, this is the coefficient of the basis element chi s. Once we move not just to a function whose inputs are Boolean, but also the outputs, then we can get, if we look at Parseval equality, that means that if we take the sum of all Fourier coefficients, that's the same as the expectation of f squared. And f squared is 1, so the expectation is 1. It means that if we look at the squares of the Fourier coefficients, these 2 to the n numbers sum to 1. We can treat them, these are positive or non-negative numbers summing to 1. We can treat them as a probability distribution over these subsets, the 2 to the n subsets. We call this the spectral distribution of the function f. So the probability of sampling a particular set S is just f hat of s squared. Okay, so this is our starting point. Now we define two values that we can associate with each function, the entropy and the influence. And both of these somehow measure how spread are the coefficients, meaning how close is the distribution to something rather uniform. So in the total influence, we care about sampling a set and looking at the expected degree, expected cardinality of the set. So it's somehow close to the expected degree of this function as a polynomial. So this is one value we care about, and the other is the Shannon entropy of this distribution. So we can just calculate this as this sum of we have the probability and the logarithm of the probability. Both of these will be high when the function is The distribution is spread over many of these sets S. And let's take an example. We take the very simple function, the OR function of two variables, and we can present it. We have 2 to the 2, meaning 4. This is the dimension, this is the number of basis elements, and we look at the coefficients. We have -1/2 and then half, half, half. If we take the squares of these, we get 4 times 1/4. These sum to 1. This is actually the uniform distribution. This is a special case. Usually OR doesn't give us the uniform distribution, but in this case, we can compute the influence. That would be the average of 0, 1, 1, and 2. And we can also compute the entropy. So the entropy is log 2 of 4. That would be n, small n. Okay, so that's an example. Any questions about these definitions? Okay, so let's move on. This is the conjecture. We said we are going to give lower bounds for the conjecture. So here is the conjecture, and it's more than 20 years old by now. It's by Ehud, Friedgut, and Kalal. And they conjectured that you could always bound the ratio of the entropy and the influence of every Boolean function by a constant. So this is some universal constant. We can also, if the function is, for example, if you take just a constant function, obviously not a constant. Let's say you take a function that is one basis element. So the distribution is very trivial. You have no entropy. This is 0 entropy, but you have some influence. So this works. And you can also consider other functions. Random function. For a random function, you probably have something like linear in n in both sides. So that makes sense. Something like 2 would suffice. And if you have a symmetric function where you applying some permutation on the input variables doesn't change the output of the function, then this was proved true. Many cases this was proved that this conjecture holds, but it's not known for the general case. And we would like to, personally, I believe this conjecture is true. So the best thing to do if you think a conjecture is true is try to, instead of trying to prove it, that's what everybody else does. So trying to disprove it may give us some ideas about how the proof should work. Let me just mention that if the function is not Boolean, then this is not true. We could take something like f of x. If we just take the proper normalization and then you take the sum of all the basis elements with a singleton set, then this function has influence, and this one is something like 1 because all of the sets are of size 1. This is a set of size 1, so the expected is size 1. But the entropy, this is uniform over log variables, so that you have something like log n. So that means that that the ratio is not constant. But when the function is Boolean, then we believe that the conjecture says that this should be a constant ratio, at most a constant ratio.
Should the logarithmic separation, is it the best possible, or is
what do you mean best possible? It is known that if you replace C by log n, then this is true for every function. And let me present the problem in a different way. Let's say we sample S, and I want to transmit S to you. So the entropy somehow means that this is the average amount of bits that I need in order to tell you which S I picked. Well, one way to do that is just tell you one after the other. If you have, let's say, 5 elements, I will just name them all the elements, all the members of the set. So if the influence measures how many members are there in the set, and I use log n bits to write a number for each of these, then I can just transmit the set itself, writing all the numbers in the set. So this can be formalized, and this is true. But we believe that the conjecture says that we can actually do this with a constant number of bits per element. You don't need to use log n bits to write down the specific element between 1 to n. All right, so what we are going to do, as I said, is lower bounds on the constant, and this is done to better understand how lower bounds should look like, so we can prove the conjecture eventually. So solving an open problem, a very old open problem is important by itself. It also has some consequences. I'll just mention this one, the Mansour's conjecture, which basically says that if the conjecture is true and you can write an expression, a not too big expression for the function, then it means that almost all the mass of the spectral distribution is just concentrated in rather few elements, not 2 to the n, not some exponential number, but just polynomially many Fourier coefficient would carry almost all the mass, just like we said here. Let's do some baby example of a lower bound. So we take the O function, but instead of 2 variables, we now take n variables. We can compute the influence and the entropy. This function is very, very not balanced. It's almost always true. So the influence, as you can see, is very small, and also the entropy is very small. But if you take the ratio, you get something that is almost 4, just slightly below 4. And this means that if you want a constant to hold universally, you need to take a constant that is it's at least 4. Otherwise, you could take n big enough, and that wouldn't work for this specific OR function. So that's a baby example. We're going to get better bounds than c equals 4. And the first bound was actually not by us. This is what started this whole research. Before that, let me just define a few more things. So I'm going to define the dual function. You negate the input and the output of the function. That gives you a different Boolean function that we call the dual. For example, if you do this to OR, you get AND. If you do this to AND, you get OR. That's the Morgan laws. And if you do it twice, then you get back the original function. And another nice thing about it is that the absolute value of the Fourier coefficient is the same. So the squares are the same, and the distribution is the same. So we get the same influence and the same entropy. So that's dual functions. One more thing would be monotone functions. So that's exactly what you'd think. But in this case, we compare the vectors coordinate-wise. So if you just flip a bit from true to false, it means that the function cannot turn from false to true. It always has to obey this direction. That turning bits on can make the function true, but it cannot make it false, and the other way around. And one more thing, if the function is monotone, then the dual function is monotone. That's if and only if. By the way, the conjecture is not known for monotone functions. That's a large class of functions for which the conjecture is not known. So we weren't the first ones to give lower bounds. There's a lower bound by Ryan O'Donnell and Liang Tan from 2013 that uses some recursion composition theorem. We'll see how it works later, because we're going to make a version of this theorem. But basically you start with some function, some balanced, meaning that the number of plus ones as the output and number of minus ones is the same, or we could also say that this means that the expected value of the function is 0, and this is also the 0th Fourier coefficient. This means balanced. If we take this such kind of function, then instead of just getting h of g divided by I of g, you can get a bit better, right? Every function would give you h over I. If you take such a function, you get slightly better because the denominator is smaller, so the bound that we get is slightly higher. So once we have this tool, we can just take some function and use it. So here's a function, and you can compute the influence, and you can compute also the entropy and get some nice bound, 6.27 something. Well, looking at this function, there's something weird. Why would you have these two clauses? It makes no sense to have one clause with x1 and one clause with not x1. And actually, it's not a balanced function. There was some kind of typo. I know exactly how it happened. It's just computing with integers instead of Booleans, but it's fixable. We can take another function with the very same parameters, and we get the same bounds. So this is a nicer function. It's also a monotone one, no negations. And we recreate the lower bound. So this is the starting point. And from here, we want to look forward and see if we can find some other function, a better function as g. And indeed we can. 7 variables doesn't give an improvement. 8 variables, we have some improvement. As you can see, we got, instead of 6.27 something, we get 6.35 something. So not a huge improvement. And I'll tell you, we're not going to get huge improvements overall. We're only going to get to something like 2.45. But that's still some progress. And we can go on and find something slightly better with 10 variables. Again, 9 variables gives no improvement. 10 variables gives us this. And here's something common to all these functions. So we have x3. It appears everywhere except the first clause. And we have x4 that only appears in the second clause. Maybe this means that presenting this as a CNF formula is not the right thing. So we'll rewrite this in a nicer way. That's a nicer way. We still have x1 and x2 at the beginning, but the rest of the expression is just this x3 or x4 and x5 or x6 and in the end of this sequence, we have x1 once again. This we can easily generalize. So this we want to write down as the conjunction of two functions. The first one is or of two variables, and the other one is this and/or. And this is a balanced function. You can compute this. If you assume that the first part is true, then with probability 2/3, the second part is true. So that makes it a balanced function. And let me also mention that there is some relation between the left and the right part, because x1 is shared, and we couldn't have in any way some version of GM that doesn't depend on x1. We cannot have disjoint support here, because we can have a function, a finite Boolean function that would give us expectation or a probability of getting 0, 2/3. 2/3 is not something that looks like an integer divided by 2 to the n. But we'll get there. Remember, this 2/3 is going to play a role soon. Anyway, we can now take m to infinity. Let's make a table. we get better and better bounds, seem to converge somewhere. We are going to get this 6.377 something. This also has a nice closed expression. So can we take the limit? Is this really the limit? We still have no proof for that, but each of the rows in this table gives us some lower bound on C. Okay, let's leave this for a moment and we'll go and explain another part of the title, lexicographic functions. So these functions go like this. I'm going to decide how in advance how many of the outputs are going to be true. Let's say I want S of the outputs, S of the 2 to the n, let's call it capital N. S of these are going to be true and the rest are going to be false. And I'm going to take the first lexicographic function that has this, meaning that all the first capital N minus S values are going to be false and the last S are going to be true. This is my function. It depends obviously on the number of variables S and also N, sorry, small n, and also on the number of truths at the output, the size of the pre-image of true, which is S. For example, if I only want one true at the end, that would be the AND function. If I want capital N minus 1 true values, meaning only one false, that's the OR function. And we can have some more nice facts. Let me just mention the last one. If S is even, then the last variable is meaningless. It doesn't affect the output. So in some sense, I can just consider a smaller function on n minus 1 variables. And if S is still, S over 2 is still even, I can continue dividing more and more. So why should we care about lexicographic functions? What good do they bring to this world of entropy and influence? So it appears that they are very related to the total influence. If we want to maximize the ratio, want to find a counterexample or some function that gives a high ratio of entropy to influence, and we want the total influence to be as small as possible. And the edge isoperimetric inequality in the discrete cube, as you can see, it's a very old result by Harper and was proved many times by some versions of, by some other people. It says that if you decide on the size of the support of the function, if you decide how many truths you're going to get, then the best way to get the smallest influence you could get is the one you'd get from the lexicographic function. So that makes sense. If you decide on your support and you want the smallest influence possible, you should take the lexicographic function. And we can get some other bounds. This is not a very good bound. It's 2p log 1 over p. It's a good bound if p is a power of 2. It's not such a good bound if it's not. So the green line means the actual bound, and the orange line is the lower bound that we get from the 2p log 1 over p. But we're going to use the actual values. One thing I want to point out in this graph, then the highest influence you could get is when p is 1/3. Same is for 2/3. That's symmetric around p equals 1/2. But if the influence at this point would be 4/3. So in some sense, it's weird because we want low influence. That's what we just said. We wanted the influence to be as low as possible to minimize it, but still we're going to see we're going to use the lexicographic function of highest influence somehow. So another nice thing about lexicographic functions is that we have a very nice expression for them. If we want to compare the input x to the number s, to the binary representation of s, that would tell us whether x is one of the last s elements or not. That would tell us whether we should output true or false. And this comparison is being done from the most significant bit until we find a mismatch. And once we find a mismatch, then we know what the value of the function should be. So we have a very nice expression. We need to read each bit only one time. And then if this bit has the wrong value, then we already know the value of the function. And only if we get to the very end, if we're very close to the boundary between the falses and the truths, then we have to read many of these bits. On average, we need to read something like 2 bits of the input. And that's a good thing because I'm going to use many variables, not just n. We're going to use infinitely many variables. So how would we do that? Instead of counting exactly how many true values the function is going to have, the size of the support, I'm going to measure the fraction of the values that are true. So this is going to be some number between 0 and 1. For example, or on 2 variables would give me 3 out of 4 times true. So the lexicographic function that works for the ratio 3/4 would be or on 2 variables. And if I want more variables, I can just add them and have them with no influence on the function itself. So I can just have these ineffective variables hanging around, but not affecting the function. One other example, which may seem familiar, is what happens if we take 2/3. So if we take 2/3, the binary representation is going to be this alternating 1s and 0s. So this means that we can get the formula for this function, and this is very similar to what we saw in this version. If we take the lexicographic function, and we take 2m-1 variables, and our p is going to be 2/3, then we get this gm. So what was gm? We'll get to it in a minute, but the logical thing now would be to take n to infinity. So this is going to be a function on infinitely many variables. Not all of them are very influential. In average, I only need to read 2 of them to compute the value of the function. So x100 is going to have very little influence on the output. I only get to read it with probability 2 to the minus 99. And since the influence and entropy both are very continuous in the Lipschitz sense, meaning that changing very few values in the function doesn't really change the influence or the entropy. So we can just say, okay, there's the infinite function. I can approximate it by some function on 100, 1 million variables, and the difference wouldn't be as large. So let's do our computations for infinite functions. They're nice. They're much more easy to work with mathematically. And then whatever we prove for infinite functions would be true also for finite functions, just that we need to approximate them. We need to trim them after some 1 million variables, and we'd get approximately the right result. Okay, I'm not getting into the exact estimation of how far can the influence, what is the amount of change can happen in the inference, meaning after we change something between the functions, but it's something that goes to 0. So that's what we really need. And we're ready to present our first construction. We already saw it in a sense. We have two lexicographic functions, one of them with p equals 3/4, that's OR, if you remember, or on two variables, that's x1 or x2. And the other one is this lexicographic function with p equals 2/3. This one depends on infinitely many variables, but if you take n to infinity, this dependence that we have x1 shared between the left side and the right side, it actually disappears. We have two separate parts here, the green part and the orange part. And if we take this disjoint conjunction of Boolean functions, we take disjoint support and we just end the two functions, it's very easy to compute the influence and the entropy from the numbers that we get for the base functions f and g. So here we can compute and get exactly what we saw in the table. If we take, we can compute what we'd get for this function and get the limit that we saw in the table a few slides ago. So this is a nice construction. You could think, how can we improve it? Maybe we find some other two numbers that we multiply and get 1/2. Remember that we need, at the end, we need a balanced function, a function whose support is 1/2 of the size of the entire set, because this is what we want to use in the recursive composition theorem. So we need to, in this case, we need to take two numbers whose product is 1/2. Trying a bit, these are the best that we could take. So we need another idea to improve upon what we have here. Questions? All right, so what we're going to do now is trying to improve the theorem. So far, we took the theorem, the recursive composition theorem, as given, and we tried to find a better function, g, to use in the theorem. And I'm not sure whether this is the best function, this g infinity that we have here, but we couldn't find a better one. So maybe it's time to change the tool. So let's make the tool not dependent on having a balanced function g. So let me tell you now how the recursive composition theorem works. We define a sequence of functions. We start with the identity function, just mapping x1 to itself. And then each time we use g to combine disjoint copies of the previous function to get the next function in the sequence. So the first function, f1 would be g, and then f2 would be g of g times g, comma g, comma g, comma g. This one would have already n squared variables, input variables, and so on. And the important thing here that we need g to be balanced. Otherwise, if we continue doing this, then the function would become very unbalanced, and we don't want that. We want the function to be balanced, meaning that if we start with f0 that is balanced, then we continue, and then f1 is balanced, f2 is balanced, each function is balanced. So let's modify the definition of balance. I don't want expectation 0 to map to expectation 0. I want expectation eta to map to expectation eta. This still keeps the same. If I start from something, we can continue and have the same value after each application. This is what we want to do. So if we look at this function, the NAND function, not of AND, this is no longer a monotone function, but it's still a nice and easy function on two variables. And indeed, you can compute a value for which this function is balanced. If you take two uniform input bits, then the output is not going to be uniform. But if they're biased with this bias, then the output would have the same bias. We can just compute this. So that means that we now can begin and do the same thing. We just compose G over itself, but we have some problem. We need to start somewhere. And we would start from some function giving us a specific bias. That would be a lexicographic function. We pick the right P to be 1 minus eta over 2. This function would have bias eta to start with, and then we can just apply G in every step and get the inductive step and take this to infinity. So we needed lexicographic functions to have the base of the induction here. What can we get from this? So we can modify our Fourier analysis. Instead of using the uniform distribution, we can use a bias distribution. We get a different spectral distribution and some modified influence and entropy. We can compute this for this NAND that we just mentioned. And we can also correlate the influence and the entropy of this function that we get from the recursion, from the bias recursion. We can get another lower bound on C. So if we do this, this is just a generalization of the recursive composition theorem. If we took P equals 1/2, that means zero balance, meaning the regular balanced, then mysteriously everything disappears and we just get this H over I minus 1. We'd get that the variance is 1 and all the other parts would disappear. But here we have a slightly more complicated version. And indeed, if we use, instead of G function, we use this NAND that we just proved, and we take the right P, the one for which NAND is balanced, and we plug in all the numbers, we get a slightly better bound. This is no longer 6.37 something something, we get 6.41 something something. And once again, this gives us an opportunity to try to change. Maybe we should take another function. Why NAND on 2 variables? Maybe there's a nice function on 17 variables that is 0.157 balanced, and we can plug it in. We tried to look for some functions. We couldn't find one that is better than this NAND. Okay, let me just say that in this composition theorem, it makes sense. Well, sorry, maybe I went back too much. So it makes sense to maybe to take a different F0. If you look at this here, if instead of taking this LP, the lexicographic function, you take a different function as F0, what you'd get is the following. On the left side, you get what you'd get from F0. So if you already have a very, very good function, if most of the gain is from the left side, the left term, then there's not a lot of things that we can get. But if you're counting on the right hand side to give you something, it makes sense to minimize the influence of F0. So that means we should choose the lexicographic function LP as our F0. Once we choose what P is, out of all these, the function whose support has this size, it makes sense to choose LP. Okay, so that's the second construction. And in this construction, we changed the tool. we improved the recursive composition theorem to generalize it to the biased case, and now we can get a better function as our base G function. So we have now two constructions, and both of them used this notion of infinity twice. In the first construction, or in each of them, we needed to use some lexicographic function, whether it was this L of 2/3 that we used in the first construction, or the one that we used as F0 as the base of the induction in the second construction. So this is one use. And the other use of the limit was when we did the recursive composition, meaning that we built a sequence of function, this F1, F2, Fm, and took m to infinity. So we had two limits. 2 is a small number. Infinity, Aleph naught, is a larger number. So maybe using an infinite number of limits would give us a better bound. Indeed, it does. It's still just, it's Aleph naught times Aleph naught, that's still Aleph naught. It's all countable, but it does give us a small improvement. So we're going to define a sequence of functions not using this recursive composition. We're not going to separate the recursive composition from the choice of the function, meaning that we define now a sequence of functions in a different way. Let's say we have some base function lambda, and we're going to define a new function kappa using this so-called equation. So I want the function kappa to satisfy this equation. It has kappa on both sides, so that's why I call it equation and not definition. And if I really want to do this, I just take the limit. I want to start with some function, let's say lambda itself, and then I take, this would be kappa 0, and then I would define kappa m plus 1 as applying this function, this lambda, this joint conjunction with kappa m, and taking the dual of all of this. We're taking this as the next function in the sequence, and we hope that it somehow converges. So in some sense, doing this a lot of times, we're going to get to the limit object for which the kappa on the left and the kappa on the right are the same. I'm not going to go into details about why this limit is attainable, why there is a limit for this function. Obviously, we can compute if such a function exists, we can relate the probability of getting true from kappa to the probability of getting true from lambda. That would have to hold just because we can apply it, we can take it from the equation. Okay, and I'm saying that this equation is somehow inspired by the NAND function because we have the and, the disjoint conjunction, and then we take the dual, which in some meaning it's similar to taking the negative, taking a not. It still keeps a monotone function. Note that if we started with a monotone function, this is still monotone. So this is something that we would use. All right, we're ready for the last construction. The third one, we're going to take the limit of limits. So we start with some f naught, and we do this basic step every time to get the next function. Remember, in each of these functions, we use the limits. And now I'm taking a sequence of functions. For each step, I need to go to infinity, and I'm taking m to infinity, so I'm actually doing this infinity times infinity steps. This looks like a terrible function to analyze, but actually the analysis is very nice. We can compute what would be the probability of each of these functions. And since we're taking, if we remember the claim from here, if we take this sequence, we take some number, and then the next number in the sequence is 1 over 1 plus the previous number, this sequence converges no matter what is the starting point. This sequence converges to the inverse golden ratio. So we know what is going to be the value, this probability of the function, as we go to higher m. And also we can multiply these q's, q0 times q1 times q2. And we have this theorem. We can compute what would be the limit of the ratio of the entropy and the influence for this function, the sequence of functions that we're building here. It has two components. One of them depends on the initial function. If you take the ratio of h and I of f naught, this is one of the things that we get. But then we get another component, and this is somehow similar to the formula that we had in the biased recursive composition. We have a very weird function, this beta function, that only depends on q0. It does not depend on the specific f naught taken, only on q0. And you have the formula here for beta. It's an infinite series. And if you look at these numbers, you have this pi k minus 1. This is going to 0. So the first terms are the most important ones. And if instead of taking infinitely many summands in the terms in the sum, if you only take 2 or 5 or 10, then you actually get a very good approximation for this beta. Okay, so once again, if you decide on q0, the most sensible function to take if you want to maximize the expression is the one that gives you the smallest possible influence of f0. So that would be, if you decide which q0 you want to take, let's take f0 to be the lexicographic function. And maybe we could actually make it that much easier if we start with the case of q0 equals 1/2. Then simply the bound that we get is beta of 1/2. When we compute it, and this gives us our 6.45 that I promised before. Okay, so that's a nice bound. Why should we take q0 equals 1/2? Does it make any sense to modify this? How does even beta look like? So here's beta. We have beta is the sum, the infinite sum, but if we only take 1 or 2 or 10 of the terms in the series and sum only these, then here you can see in the graph how this approaches the beta. So if you take 10 terms, this is already very, very close to the shape of beta. And one more thing that you could see, if you look at beta 1 or beta 2, this is not symmetric. There's a very, very slight bias towards numbers between 1/2 and 1. And actually the maximum is achieved not at 1/2, but really slightly above 1/2 at some q0.501 something. And you get really a tiny more than beta of 1/2. The only problem is that if you choose this q0 instead of 1/2, then at the end we're going to lose, because the influence of the lexicographic function is going to be more than 1, and the variance is going to be to give us some entropy, and this means that this entire expression here, if this one is greater than 1, we're not going to win a lot. So beta of this Q0 is slightly more, but everything that we got, we lost by having this a positive number and this something that is greater than 1. So we shouldn't do that. Again, if we have some better F0, one that gives us a better bound, we do not know. But among all that we've tried, this is the best that we could do.
Rani, so
yes.
By your requested a few more minutes.
Okay, that's good because I'm very close to the last slide.
Okay, great.
This is the last slide, as you can see, the almost last one. There's also a thank you slide in a few more seconds. So let's summarize what we got. So I showed you 3 lower bounds on the value of C. Assuming that the conjecture is correct, then C cannot be smaller than this 6.45 something something. All of these somehow use lexicographic functions. Is this the best we could do using lexicographic functions? I'm still not sure. Obviously, we did 3 improvements, so there's a good chance that there's a way to get a 4th improvement. So maybe we could get slightly more using the similar methods. We would need some new ideas, but maybe we can improve this a bit. If you can see, in absolute terms, this is not much of an improvement. O'Donnell and Tan got 6.27. I'm showing you 6.45. That's a very tiny improvement, but still there are some new ideas here. And one really big problem here is that in all these ideas, actually what we get, the functions that we get are called the read once formulas. These are functions for which you don't need to read the value of an input variable more than once. You only need to read it once. And after you did that, you don't need to read it again to compute the value. And it is known that for such functions, actually the conjecture holds. It holds with C equals 10. So whatever we do, if we try to improve this, we need some idea that is able to overcome the read once formula obstacle. So maybe 6.45 would be improved to 7, to 9.9, but we cannot pass the 10 without a completely new idea. One more point is that the middle construction used the NAND, but the other 2 constructions used monotone functions. Maybe it's sufficient to prove the conjecture only for monotone function. Is it as hard as the general conjecture? Our lower bounds hold even if you consider only the monotone case. So maybe thinking of monotone functions is the way to go. One more take-home message here is that these lexicographic functions, besides our minimizing the total influence, they seem to be very, very relevant for the conjecture, and maybe understanding more about these would help us prove the conjecture. As I said, as C believes the conjecture is true, trying to play the devil's advocate and provide a lower bound is a method for us to try to understand how we can prove the conjecture. And maybe one technical point, I reminded you that we can all do this infinity and infinity of infinities tricks because we have some Lipschitz continuity, and in the proof that we had some bound that is optimal for the total influence, the bound of what is the change that we can expect in the influence if we do some change in the function. So the estimation that we had for the total influence was exact, as a worst case. And for entropy, we got something which is not optimal. There is some difference between what we could prove and what the lower bound that we have. So there's a slight room for improvement if you care about this part. Thank you very much for staying and listening to the talk. If you have any questions, I'd love to hear these.
Thank you very much, Rani. It was a wonderful talk. So are there any questions?